Saltwater desalination systems work in one of the most corrosive environments in industrial processing. Constant exposure to salt-rich seawater, high temperatures, and turbulent flow conditions accelerates material degradation, leading to pitting, crevice corrosion, and stress corrosion cracking. When components like filters, piping, and heat exchangers fail prematurely, it results in expensive downtime, increased maintenance costs, and reduced overall system efficiency. To combat these challenges, engineers must select materials with superior corrosion resistance. While 316 stainless steel is often used as a baseline, it lacks the durability needed for long-term performance in aggressive saltwater conditions. Alloys such as Avista 254, 904L, and duplex stainless steel offer significantly better resistance to localized corrosion and mechanical stress, making them ideal for desalination infrastructure. So desalination systems, such as reverse osmosis, operate under extreme conditions that accelerate corrosion. High salinity, elevated temperatures, turbulent flow, and dissolved oxygen create an aggressive environment for metal degradation. Chloride ions in particular penetrate protective oxide layers on stainless steel surfaces, initiating localized corrosion such as pitting, crevice corrosion, and stress corrosion cracking. And what's worse, these forms of corrosion are often invisible until significant damage has occurred. Corrosion directly impacts system performance. For example, scaling and corrosion on heat exchanger surfaces reduces thermal efficiency, increasing your energy consumption by up to 15% per millimeter of scale. In reverse osmosis systems, corrosion of membrane housings and pipings can lead to pressure drop, reduced permeate flow, and compromised water quality. These inefficiencies translate into higher operational costs, more frequent maintenance, and potential system shutdowns. And beyond performance, corrosion poses serious safety risks. Stress corrosion cracking and high pressure components can lead to an increase in sudden failures, risking personal safety and environmental contamination. In desalination plants, failure in brine reject lines, pump housings, or storage tanks due to chloride-induced corrosion have been documented, often requiring emergency repairs and replacements that can have major costs for your system. Using 316 stainless steel as a minimum standard is increasingly seen as inadequate for long-term durability in desalination environments. While 316 offers moderate resistance to chlorides, it is prone to pitting and stress corrosion cracking under high salinity and temperature conditions. Upgrading to higher performance alloys such as Avista 254 SMO, 904L, or duplex grades significantly improve corrosion resistance, mechanical strength, and life cycle reliability, reducing the total cost of ownership and helping to enhance your plant's safety. Avista 254 SMO is a super austenitic stainless steel designed for extreme chloride-rich environments. With a high molybdenum content, elevated chromium, and nitrogen, it achieves a pitting resistance equivalent number of greater than 43, making it highly resistant to pitting, crevice corrosion, and stress corrosion cracking. Its mechanical strength of RP 0.2 is nearly double that of 316 stainless steel, and it maintains excellent ductility and weldability. These properties make it ideal for desalination components like heat exchangers, brine reject lines, and seawater intake systems. 904L is a high alloy austenitic steel with elevated nickel and molybdenum content. It offers strong resistance to sulfuric acid and phosphoric acids, as well as chloride-induced corrosion. While not as robust as 254 SMO, it provides a significant improvement over 316 in terms of corrosion resistance and is often used in less aggressive zones of desalination systems. Its usual good lower cost and weldability make it a practical choice for budget-conscious upgrades. Duplex grades like 2205 and Super Duplex SAF 2507 combine the benefits of austenitic and ferritic structures. They offer high strength, excellent resistance to chloride stress corrosion cracking, and good weldability. Duplex alloys typically have a Pren of 35 to 40 plus, making them suitable for structural components, high pressure piping, and reverse osmosis membrane housings. Their lower nickel content also makes them more cost effective than super austenitic grades, while still outperforming 316 in durability and lifespan. 316 stainless steel contains only 2 to 3% molybdenum and has a Pren around 25, which is insufficient for long-term exposure to seawater. It's prone to pitting and crevice corrosion, especially in high temperature and high salinity conditions. While it may be suitable for low-risk components, its use in critical areas often leads to premature failure, increased maintenance, and safety risks. Upgrading to 254 SMO, 904L, or duplex alloys ensures better performance, reliability, and lower life cycle costs across the board. Each alloy has strengths that make it better suited for different parts of a desalination system. Avista 254 SMO is ideal for components exposed to high chloride concentrations and turbulent flow, such as brine reject lines, heat exchangers, and filter elements. While seawater intake screens are critical for system performance, they typically encounter low chloride exposure, as chlorides are introduced later in the process. Its high Pren and resistance to stress corrosion cracking make it a top choice for long-term durability. 904L, while slightly less resistant, is often used in lower pressure zones like pre-treatment piping and chemical dosing systems due to its cost effectiveness and good weldability. Duplex stainless steels such such as 2205 and SAF 2507, are preferred for structural components like reverse osmosis membrane housings and high-pressure piping, offering a balance of strength and corrosion resistance. Material selection is often a trade-off between upfront cost and life cycle performance. 316 may appear to be economic initially, but its susceptibility to pitting and crevice corrosion leads to frequent maintenance and early replacement. 904L offers a moderate upgrade with better corrosion resistance and lower nickel content than super austenitic grades. 254 SMO, while usually more expensive, delivers superior performance in aggressive environments, reducing downtime and extending service life. And duplex alloys provide a good middle ground as they have a lower cost than super austenitics, but have excellent mechanical strength and corrosion resistance, especially in high pressure zones. The operating conditions of a desalination plant, which includes temperature, salinity, flow velocity, and chemicals used in cleaning, should be the main guide for alloy selection. Thermal desalination systems require materials that have high thermal conductivity and resistance to scaling and corrosion, making 254 SMO and duplex ideal. In reverse osmosis systems, high pressure and brine exposure is common, so duplex alloys excel due to their strength and resistance to chloride-induced stress corrosion. Plants in tropical or polluted coastal areas may also benefit from super austenitic grades due to their enhanced resistance to biofouling and aggressive seawater chemistry. Ultimately, the right alloy depends on the specific application, budget, and performance needs, and expected lifespan of each alloy. Partnering with experienced suppliers helps to ensure that woven wire mesh components are manufactured with the optimal material for each use case. By upgrading from 316 to advanced alloys, desalination systems can achieve greater reliability, safety, and cost efficiency over time. Thanks so much for watching. If you have any questions, click on our Talk to Us button to get in contact with our many experts on woven wire mesh. And if you'd like to learn more about woven wire mesh or our many products, we have a learning center filled with written and video content to make you an expert. We also have a YouTube channel. And don't forget to click that subscribe button and ring that bell to keep up with all things WS Tyler. Once again, my name is Andrew Kotlar, and I'll see you around in the next video. Bye for now.